We are now starting our lecture, which is the second one on TE 1103, Electrical Engineering Circuit Analysis. In the previous lecture, we talked about the basic concept in electricity, basically the issue of electrical components. We explained the passive and the active components, and we said the passive components, they have a voltage drop across them. That means when the current enters a passive component, it enters through the high potential side and then it leads with the lower potential side, hence the down in concept. And in an active component, we say the current will enter through the more negative side and then it leaves through the positive side, like you see in a battery. That's the upward concept. So today we are now looking at the electrical quantities, and I will share the slide as we go, right? So that is our second lecture, electrical quantities and measurements. And this one was done in 2017. And, now, the first thing that we have to talk about when you look at electrical quantities is the issue of standard units or international standard units. So basically, we have 7 basic units which measure length, and we have the meter as length, mass in kilograms, time in seconds, electric current in amperes, thermodynamic temperature in Kelvin, luminous intensity in candelas, and charge in coulombs. So you realize that all other units, they basically can be expressed in terms of these 7 base units. I'm sure we know that from our A-level physics and other subjects, right? So all other units are derived from the 7 base quantities, like I just said. Then, when you relate now quantities in terms of the formulae that we use in our studies, you realize that each quantity should have the proper unit of measurement as defined in the equation. So if you put the wrong units in an equation, it means the quantity that you calculate might be wrong, mainly in terms of the value or the units that will come out. So every quantity must have proper units of measurement as defined in the equation. Then you use the proper magnitude of each quantity defined by the defining equation. So if they say are given 100, you should know whether it's 100 meters or 100 centimeters, so that your calculation will not include a wrong multiple of the given quantity. Then you should use the same system of units for each quantity as defined in the equation. So what we are saying is that when you are given an equation, there are a lot of units that we talk about. There are the metric and other units. So when you are given the equation, you should know whether you are using the standard international unit or you are using the matrix, so that at the end of the day, you'll be able to calculate properly. So again, that is determined by the defining equation. Meaning to say, if the defining equation is not in the standard international units, then you should put in a factor which shows that you are now using the SI units in your equation, right? Then the magnitude of the result should be a reasonable nature when compared to the level of the substituted quantities and normal levels. So what you are saying is there's a certain time when you make a calculation, and then what comes out there will show you whether the units used were correct or were wrong, right? So as an example, you realize that sometimes when you use the wrong unit, then you also will get a wrong outcome from that, right? And in that case, when you use the correct unit, then also your result will become correct. So let's say, for example, someone asks you, how tall are you? Then you say 187 meters because you calculated your height and you just said someone saying 187. It is correct when it's in terms of centimeters, that is 187 centimeters, 1.87 meters. But then when you use the wrong quantities, then it becomes meaningless or unreasonable. Then the next thing that we want to talk about is the concept of charge. So when you talk about charge, that's the one which we use in explaining many principles of electricity. Charge is the basic quantity in electric circuit. So charge is defined as the electric property which gives an atom its properties and is measured in coulombs. So we know from our basic knowledge that an atom is made up of protons, neutrons, and electrons. And then in this case, we know that the charge of an electron, which is the basic unit of charge now, becomes about minus 1.602 times 10 to the power minus 19 coulombs. And a coulomb is 6.24 times 10 to the power 12 electrons. So you can see that 1 coulomb is basically a very big unit of charge. And since we said charge of an electron, and the electron becomes the smallest unit, then it means all values of charge should come in as integral multiples of the charge of an electron. And charge can neither be created nor destroyed. So that's the basic concept about charge, right? Right. It's another and the background noise there. Can someone mute their? Can someone mute their audio then? It's giving some interference. Thank you. So as explaining the concept of charge. So charge, that's the basic unit that we are using. And now when we are talking about charge in an electrical circuit, we are talking about the flow of electrons. Because as you know, in the atom, the protons and neutrons are bound by the nuclear forces. So in an electric circuit, you show that the flow of electrons is what we take as the flow of charge. So in our circuit, electrons, since they are negatively charged, they will flow towards the positive terminal. But now the conventional electricity flows in the opposite direction. That means our electricity will flow from, this is the flow of electrons, right? And then the electricity will be flowing in an opposite direction. So let's do that again. So as you can see, our electrons, they are repelled from the negative terminal. They go through the circuit and they go back through the positive terminal. But then when you talk about the flow of current now, the flow of current is opposite the flow of electrons. So current will flow from the positive terminal through the circuit to the negative terminal. So let's not confuse the flow of current with the flow of electrons. So current flows from the positive into the circuit and back through the negative. But electrons flow from the negative back through the positive terminal. That's a very important thing to note. Right. Then electric current exists when there is movement of electric charge. So when you talk about electric current, we are saying there should be movement of charge. If there's no movement of charge, then there is no current flowing. If you remember from the previous lecture, we said now the current will flow from a higher potential to a lower potential. That is also what we use to determine whether there is a current or not. So when there is no movement of charge, there is no current to talk about. So current is measured in amperes, and the ampere is the time rate of flow of electric charge. That is, if we say charge is called Q, then current I is called dQ by dt, rate of change or flow of charge. We say the time rate because there can be different things that can cause charge to flow, but we are saying the rate of change of charge with time is what we call current, and Q is the charge in coulombs. If the current does not change with time, it is called direct current or DC, meaning to say if it is just current that does not change direction, then we call it direct current. We use uppercase to represent DC quantities and lowercase to represent time varying quantities. So you realize that in this course, we'll talk about direct current, DC, and also we'll talk about alternating current, which is AC. So DC, it does not change with time. AC changes with time, either it changes magnitude or it changes direction, or it can change both. That is the concept of DC and in the AC. So when we talk about DC, we're saying it doesn't change direction, just like the movement of that ball, right? Then AC, it will be changing direction and magnitude with time. That becomes alternating current, right? So current is a vector quantity. It has both magnitude and direction. So it can move in that direction, and we are saying it's plus 10 amperes. If it moves in the opposite direction, then you say it's minus 10 amps. So if you are given a standard direction of flow of current, then it's either positive or it's negative, showing that current is a vector quantity with both magnitude and direction. So as an example, let's see how we can use that previous formula to calculate the current. So the total charge entering a terminal, is given by Q 5t sin 4 pi t in millicoulombs. What is the current at t is called 0.5 seconds. So in our solution, we will notice that current is called the rate of change of charge with time. So dq by dt, that's our current. So our Q now is given by 5t sin 4 pi t in millicoulombs per second. And then dq by dt, it means we are now differentiating 5t sin 4 pi t from your calculus. Then you find out that the result will be 5 sin 4 pi t plus 20 pi t cos 4 pi t. Then at t is equal to 5, that means you are now substituting for 5 in the expression for current. Then I becomes equal to 31.42 milliamps. So that's how you calculate your current given how the charge is changing with time. And remember, since we said the charge is in millicoulombs, then our current should also be in milliamps. So now, since we said current is the rate of change of charge with time, so if less charge flows per unit time, then we are saying there is low current. If we have more charge flowing per unit time, then we are saying there is more current or high current, right? Let me add some other people who are coming in.
Yeah.
Right, as you come in, just mute your audio so that you don't interfere. Then we talk about voltage. So we talked about current, which is the rate of change of charge. Yeah. We talk about voltage, which is the law. Can you mute your audio? Can you mute your audio? Right. So we're talking about now voltage. So charge moves after gaining energy from a source of EMF. So EMF, that's the electromotive force, which is the force required to move a unit of charge through a circuit. So the battery is the common source of EMF in DC circuits. That is the voltage source which causes the potential difference between 2 points in a circuit so that charge can flow. Remember, in our previous lecture, we said that current will flow from a higher potential to a lower potential. But then that higher and lower potential can only be introduced when you put a voltage source. The voltage source is a positive and a negative terminal. So the positive terminal becomes our high potential, the negative terminal becomes our lower potential. Then current will flow from the higher potential to the lower potential. And that movement is due to the gain of energy by the charge. The energy being supplied by our source of EMF, right? So if there is no potential difference, then we don't expect current to flow because it will be like a flat plane. So now the voltage is the work done in bringing a unit charge from one point to another in a circuit. So that work which the source of EMF does to bring a unit charge from one point to another is our voltage, right? So voltage is measured in volts and it is equivalent to joules per coulomb. Remember I said work done per unit charge. So volts are also equal to joules per coulomb, right? So in that concept, if you take 1 coulomb through that plane from point A to B, remember when you're talking about potential energy in your physics, you talk about the perpendicular height that you gain. Then you can also, it's the same as moving the same coulomb from A to B in a vertical direction. And then the voltage, with the work done, will be equal to 30 joules, and the voltage now will be equal to plus 30 volts. That means you have moved the charge from a lower potential to a higher potential. It has gained energy, so the voltage is a positive, right? But then if you move the same coulomb from a higher potential to a lower potential, the same as moving it again from B to A in a perpendicular direction, and then the work done is minus 30 joules. That means it has lost energy by going to a lower potential. Then the voltage VBA is equal to minus 30 volts. So if you check closely, you realize that VAB is equal to 30 volts, but VBA is equal to minus 30 volts, right? So that is also very important when you look at our electric circuits. You should know the difference between a voltage gain or a voltage drop. That will be very useful when we do our circuit analysis. So a voltage drop is when the charge or the current moves from a higher potential to a lower potential. Voltage gain or a potential increase will be movement from a lower potential to a higher potential point. So that is how we differentiate between those, and it's very important for us to remember. So that's the concept of voltage, work done per unit charge, right? So terms used in the subject of voltage, there are many terms that are used when we are talking about voltages. One, we talk about potential. Potential now is the voltage at a point with respect to another point of reference. And our typical point of reference is the ground, which is defined as the zero potential level. So the potential difference now will be the algebraic difference between the potential at one point and the potential at another point. So the algebraic difference between that becomes our potential difference. Then the voltage, when isolated like potential, is the voltage at a point with respect to some reference point such as the ground, right? So when you talk about voltage on its own, it will be almost the same as potential. But as you go through the course, you realize that there are different instances where you use voltage and also where you use the word potential. Then the voltage difference again is the algebraic difference between voltages of one point and the other. So the voltage rise or drop is a terminology that will be suggested as the voltage difference. So say when there's a voltage rise, we are saying they're moving from a lower potential to a higher potential, or from a lower voltage to a higher voltage. Then voltage drop, we are moving from a higher voltage to a lower voltage. Again, these are very important concepts that we'll be using in our circuit analysis. Then go on to the EMF, which is the electromotive force, which is the force that establishes the flow of charge, right? So that force which gives energy to the charge so that it can flow becomes our electromotive force. Electricity or charge, motive, there's movement there. So that force which causes the movement of charge is called the EMF. And this is normally associated with voltage sources or sources of energy. So normally we talk about their EMFs rather than any other quantities. So the terms are sometimes interchanged, but this may cause inaccuracies. So sometimes you have to be very careful when to use the term voltage drop and when to use the term potential drop. But again, we will clarify this as we move through the chapters. So voltage now, we have an example. The EMF of a battery is 22.5 volts. How much charge flows if the energy transferred is 90 joules? What is the current if the transfer time is 1.5 minutes? So in this question, we're just trying to relate voltage to work done to get charge. And then after getting charge, we also want to get the current using charge and time. So what I normally do is I would first state the quantities which are given in their respective symbols. So say W is got 90 joules. I'm saying the work done is got 90 joules. V is got 22.5 volts, so the EMF is 22.5 volts. T is got 1.5 minutes, which is got 90 seconds. The reason why I use 90 seconds is because the SI unit of time is the second. So you'd rather convert that to second before you start calculating. Remember what I said, if you use 1.5 minutes, then that means the value of the charge that you get will be wrong. So we know that Q is called W over V. That means charge is called work done over the voltage. Or we said voltage is called work done per unit charge. You can rewrite this equation according to the requirement. So our charge becomes called 90 over 20.5, which is what, 4 coulombs. So if we calculate our charge, then what is the current? Current is called the charge per unit time. So we say charge 4 over 90 seconds, when we get our 44 milliamps as the current that is flowing in the 1.5 minutes that the transfer occurs. Then voltage and current are important in quantities, but most devices are rated in terms of the power they either dissipate or supply. Right? Let me tell the people. So you realize that very few electrical equipment has a rating in voltage or current. In most cases, they talk about the power dissipated or the power supplied, right? But then power is defined as the time rate of expending or absorbing energy measured in joules per second, and the unit is given as the watt. So the rate of dissipation or absorption of energy gives you the power developed at a certain period of time. So what it means is there should be use or supply of energy for us to talk about power, right? Then by taking the definitions of voltage and current in terms of charge, power is called dW by dt, right? Then if you just multiply by dq over dq, which is the same as multiplying by 1, by then putting dq below dw and dq above dt, dw by dq becomes called voltage work done per unit charge, and dq by dt becomes called charge per unit time. That means power becomes called voltage times current. So that is the derivation of the expression for power. Voltage times current. But you realize that this is just straightforward with voltage times current when you are talking about a DC circuit, whether you are using direct current. When it becomes an AC circuit, there are other things that we'll put in. Those two will be multiplying voltage and current by the other units that come into play. So power is positive if the element absorbs energy. That means if current enters through the positive terminal, right? And we know that current enters through the positive terminal only in passive components. So our passive components are the ones which have positive power, right? Then it is negative when the element releases energy. That means when current leaves through the positive terminal. And from our previous discussion, we know that current leaves to the positive terminal in the active components. So the battery develops negative power, and the let's say the heater develops positive power because it absorbs power. So that is how we use it there. So in that example, current moves from the positive to the negative, and the current is 3 amps, and the voltage drop across that element is 4 volts. So the power there is 12 watts. But in this case, case number B, current is entering through the positive terminal and leaving through the negative terminal. Then that means the power developed is also negative, but it's still 12 watts. Right. Then in that case, in the next case, again, we're developing 12 watts, but then again, the units, they will be different because in one point, current is entering through the negative, and another point it's entering through the positive. So that is the releasing power. Right. So I have a signal that we are left with 10 minutes. So I'll just see where we will end. Then we start another session if all allows. So in an electric circuit, the algebraic sum of power should always be equal to 0. In other words, in a circuit, the power supplied to the circuit should be equal to the power dissipated by the circuit. This comes from the law of conservation of energy, that you can neither create or destroy charge. Right. So power supplied is called power absorbed. Energy is the power supplied or absorbed over a period of time. That means our energy becomes power times time. When the power is, the time is in seconds, this is straightforward expression there. Power companies, they measure in multiples of joules given as kilowatt hours. So if you look at watt hour, that's energy, but they use the kilo, so that the unit that they use in their billing is now 1,000 watt hours. So that's another unit that they use there, but still you realize that they will be charging you for the energy that they supply to you. For example, if a stove draws 15 amps when connected to a 240 volt line, how long does it take to consume 180 kilojoules, right? So the power rating now will be the current times the voltage, which gives us about 3.6 kilowatts. To absorb 180 kilojoules, that means we are saying it should absorb 180 kilowatt seconds. So time becomes called 180 over 3.6. Remember, we have kilo here and we have kilo there. So I left with watts and watt seconds. And our solution becomes called 50 seconds. Take note of the fact that we converted our power to kilowatts so that we can easily work with the kilojoules that we get there. Or we could have converted the kilojoules to simply joules. Then we could not have converted the watts to kilowatts. We just left it as watts. And when we do our calculation, it will come out clear. This one is getting what I'm saying there. Right. Then the other component that we talk about is efficiency. Right. So we know that the power that is not always used for work. Right. So some energy is lost in different forms. We know the forms of energy that we lose. So that is our supply. Then as we move through the circuits, power is lost, right? So that energy will be lost from 1.2 So what is efficiency now? Efficiency will be what you get as the output over what you've put as the input. So it will be this guy over that guy. That will be your measure of efficiency of the system. In other words, efficiency is the ratio of the output to the input, which is given as neta, that n is output over input. And sometimes, since you know that input is got output plus losses, you can also say efficiency got output over output plus losses. Efficiency is given as a percentage, so you multiply by 100%. Remember, 100% is equal to 1, because percent means of 100. So they are just trying to put it in percentage units. Right. So our next point will be on circuit elements. But as of now, let me stop this and restart the session again so that we can go into the next step. We start with circuit elements. So we can just end this class because my minutes are over in this Zoom. Then just hold on. I'll create another one and you join again and we proceed from there. Are we clear? Right. So let's wait a bit. Then I'll come back with another session. Thank you.